Hello students, welcome to the online lecture series of Basics of Computer Network. Myself, Assistant Professor Mr. V.R. Vadekar from Department of Electronics and Telecommunication from Matoshi College of Engineering and Research Center, Nasik. Today, we are going to start a new topic of second unit, that is error detection, correction and data link control. So today we would discuss about error detection. So let's start with our today's lecture. But before starting our today's lecture, let's have a quick revision. In last lecture, we have studied about selective repeat ARQ, which comes under noisy channel. In selective repeat ARQ, we have seen if the particular frame is damaged or corrupted or being lost, so we are going to retransmit only that frame only. So that's why its name it is called selective repeat ARQ. So which has advantage over your go back and ARQ. So today we are going to start a new discussion with error detection and correction and what is linear block codes. So talking about error detection, as we know students, whenever bits flow from one point to another, they are subject to unpredictable changes because of interference. And these interferences, it is going to change the shape of the signal. And some applications require that those errors, they need to be detected and corrected. Because due to these interferences, the data get corrupted. So let's first discuss some issues related to this error detection and corrections. First, we would talk about the types of errors. Now the term single bit error, it means that only one bit in the data unit it has changed, such as your byte, your character or packet. So that could be from 1 to 0 or 0 to 1. So you can see on the screen that while transmitting, we are going to send the data 000, 000, 10. But when the receiver it has received the data, you can observe it on this shaded region that instead of a 0, 1 it has been received. So this is called a single bit error. Now talking about a burst error. The term burst error, it means that 2 or more bits in the data unit have changed. Again, it could be from 1 to 0 or 0 to 1. So this is the figure, and remember, a burst error, it is more likely to occur than a single bit error. Because guys, the reason is the duration of noise signal is normally longer than the duration of one bit. Which means that when noise it is going to affect the data, it is going to affect a set of bits, not a single bit. So the number of bits, that is affected, it depends on the data rate and the duration of a noise. So you can observe it over here. While transmitting, we would like to transmit 0, but at the receiver section, instead of a 0, 1 it has been received. Similarly, over here also 0 it has been transmitted, but while receiving 1 it has been received. Over here also 0 is changed to 1, and at the last also this bit 0 it is changed to 1. So if you can find the length of the burst error, it is of 8 bits. How we are going to calculate it? Basically, we are going to calculate it, we are going to measure it from the start of the bit where the corruption it has been started. So this is the first bit where the corruption it has been started. And now we are going to measure the last bit which get corrupted. So this is the last bit which get corrupted. So irrespective of the bits in between this first and last bit, whether they are going to corrupt or not, we are going to include this bits for measuring the length of the burst. So if you are going to measure the length of the burst, you can find it. It is of what? How many bits it is? It is of 8 bits. Now, in modulo n arithmetic, we use only the integers in the range 0 to n minus 1. As in the previous lecture, I already explained you about this one. So suppose is equal to n, n is equal to 2. Then what could be the sequence number? Then it is what? 2 raised to 2, that is equal to 4. So sequence number, it would be 0 to n minus 1. Sorry, n over here is equal to, n is equal to, I'll just make a correction guys, correction over here. Suppose m is equal to 2 over here, 2 bits, m is equal to 2 bits, and whereas capital N is equal to 2 raised to m. So it is nothing but your 2 raised to 2, which is equal to 4. So now we are going to use the sequence number in modulo n arithmetic, that is 0 to n minus 1, that is 4 minus 1, that is equal to 3. So we are going to give the sequence number 0, 1, then we are 2, and this is 3, and again the sequence number it is going to repeat like 0, then 1, then 2, then 3, and so on. Now basically guys, in this lecture we are going to divide the coding schemes. Coding schemes, basically it is used to give the redundancy. What is redundancy? In order to detect and correct errors, we are going to add some or send some extra bits with our data, that is called a redundancy. So redundancy is achieved through coding schemes, and this coding schemes it is divided into two broad categories, that is a block coding and convolution coding. So basically this convolution coding it is more complex, so beyond the scope of this syllabus. So we are going to focus on block coding. Now, as I already told guys, that the central concept in detecting and correcting error is a redundancy. Redundancy, it means we are going to send extra bits. So in block coding, we are going to divide our message into blocks. Each block it is of how many bits? It is of k bits. So these are called what? Data words. Now we are going to add our redundant bits to each block to make the length n is equal to k plus r. Then what is this resulting n bit blocks? It is nothing but your code word. So code word is equal to what? Data word plus redundancy, redundant words or bits. Now these extra bits, this redundant bits, are chosen or calculated by predefined algorithm. Now, if message it is going to divide it into number of blocks and each block it is of k bits, then how many data words could be created from this k bits? So that is 2 raised to k data words. Whereas with n bits it stands for the code word. So how many code word we can create it? It is nothing but your 2 raised to n code word. So you can see over here that n, small n, is always greater than k bits, that is a data word, because n is equal to k plus redundant bits, that is r. So a possible code words is always greater than, larger than the number of possible data words. So you would get the clear concept from this table. So suppose k is equal to 2. So 2 raised to 2 in the sense what? 4. So 4 data words are possible and each data word it is of what? 2 bits. So we have 4 data words, word 0 0, 0 1, 1 0 and 1 1. And over here, instead of transmitting data word, we are going to transmitting it corresponding code word. And you can find it that n is equal to 3. It means over here r is equal to what? 1. That is a redundant bit. So what are the possible combination? 2 raised to 3 is equal to how many? 8. So you can see this, guys, 8 possible combinations are possible for this code word. So out of these, you can observe it. For 00 we are going to transmit as 000, which is called as a valid code word. For 01 we are going to transmitting it 011, which is a valid code word. For 10 we are going to transmit it 101, which is considered as a valid code words. And instead of 11 we are going to transmit it 110, that is a valid code words. So out of 8 possible combinations, guys, we have considered 4 possible combinations as valid code word. And remember, this block coding process is 1-to-1. That is, the same data word is always encoded as the same code word. And the remaining code words, remaining these 4 code words are called what? Invalid or illegal code words. So please remember this one. And also remember this example, that because in further slides for the example we are going to consider this code word, that is for transmitting 01. The code word it has been sent, it is 011. And please note down this table, guys, because in further examples I am going to use this table, referring table 2.1. So you can also draw this table. And remember, 000, 101 and 110, it is present in the 10. So it is called valid code words. So note down these valid code words. So we would move further. So in our previous table, we have considered k is equal to 2 and n is equal to 3. So we have seen that 2 raised to k equal to 4 data words are possible, and 2 raised to n, that is 2 raised to 3, is equal to 8 code words are there. Now we saw that 4 out of 8 code words are used for message transfer, that we call it as a valid code words, and rest are either used for other purpose, which are also called as invalid or illegal code words. Moving further, this is a process of error detection in block coding. So as we know, guys, that data word it is of k bits, and code word it is of n bits. So definitely we required some generator to convert k bits into n bits or to add a redundancy to this data word. So basically generator it is going to help out in this one. So when n is equal to that is k plus r, when it is going to transmit it as a code word, it is received by the receiver and the received code word it has been given to the checker. Now if the received code word it is same as that one of the valid code words, then the word it is accepted over here. We are going to extract the data word from the code words. But if the code word sent to this receiver, it may change during the transmission or corrupted during the transmission, and due to this change that is not present in the valid list, then that it is discarded. It is simple. But one more possibility it is there, guys, that I would discuss it. That suppose if the code word is corrupted during the transmission, but the received word it is still present in the valid code word, then this error it remains undetected. So you would came to know about this one. So as I told guys that focus on that one, that data word 01, we are going to transmit it as a code word 011. So which is present in what? Valid list. Now considering the following cases. So guys, if the receiver it is going to receive 011, then definitely it is a valid code word. So the receiver it is going to extract the data word 01 from it. So no problem in that one. Second case it is guys, if the code word is corrupted during the transmission and 111 it is received, but you have referred from this table, you can observe this table number 2.1. That 111 it is called as a illegal or invalid code word. So hence it is not a valid code word. So this code word is discarded. But main problem over here is that if the code word is corrupted during the transmission and 000 is received, guys, and as you know that 000 it is what? It comes under what? Valid list, valid code word list. So it is a valid code word. Then the receiver incorrectly extract the data word as a 00 because two corrupted bits have made this error undetectable. Although the error it has been incorporated into this bits, but it is undetectable due to these two corrupted bits. So hope so you understood this problem. So this is that table that I told, that 01 if it is going to received as 011, no problem. If 01 it is received as a 111 which is not present in this valid code word. Basically this is a list of what? Valid code words. So we can detect the error. But problem over it is there that if instead of 011 000 it has been received, then receiver would think it comes under a valid code word, then it is going to extract the data 00 from it. But 01 it has been sent. It means error it has occurred, but it is undetectable. So an error detecting code can detect only the types of error for which it is designed, and the other types of errors that we just discussed may remain undetected. Now guys, instead of a 3 bits code word, let's add a more redundant bits to see if the receiver can correct an error without knowing what was actually sent. So for this guys, you required a table 2.2. So just please refer this table, draw the table in your notebook so you can refer it. So I am going to add a 3 redundant bits to your 2-bit data words so that it is going to make what 5-bit code words. So instead of 3-bit code words, we are going to see now 5-bit code words, because we want to check that if I am going to add more redundant bits, whether the receiver can correct an error without knowing what was actually sent. So let's see guys. So just refer this table guys, because I am going to take this example that for 01 we are going to receive this bits as a 01011, and these are the code words which comes under the valid code words. So please note down guys, and whatever the rest of these code words we receive, that would come in what, in illegal or invalid code words. So let's start. So assume the data word 01, it has been sent 01. So the sender, it is going to create a code word 01011 that I already told. So if this code word is corrupted during the transmission, and suppose 1 bit it has been changed, that is 1 it changed to 0, so we are going to receive it as a 01001. So as we know, 01001, this code word is not present in the table. It means it is invalid or illegal code word. So it means error has occurred, and also the receiver, assuming that there is only 1 bit it is corrupted, so now uses the following strategy to guess the correct data word. So what is the strategy? Let's see that. So comparing the received code word with the first code word in the table, that is 01001 versus all zeros, then receiver, it is going to decide that the first code word is not the one that was sent, because there are 2 different bits are there. We are going to assume it was a single bit error, but since 2 bits are different, that is 2 ones over here, then it came to know that first code word, it doesn't matches with this one. Secondly, by the same reasoning guys, the original code word can't be the third and fourth one in the table. So if it is not first, if it is not the third and fourth one in the table, then what is remained? Then the original code word must be the second one in the table, because this is the only one that differs from the received code word by 1 bit. Because it was valid code word, what? It was 01011. So what is changed? Only this bit it has been changed. Then receiver replaces this 01001 with 01011, and from there it is going to consult the table to find the data word 01, or extract the data word 01 from its code word. So in this manner, if we are going to add more redundant bits, then we can correct the error. Now, Hamming distance. Now, one of the central concept in coding for error control, it is the idea of your Hamming distance. What is Hamming distance? It is the distance between the 2 words of the same size. Remember the word that is of same size. It is a number of differences between the corresponding bits. And the Hamming distance between the 2 words, suppose X and Y, is denoted as small d in bracket, that is X comma, it is Y. So we have to find the number of differences between these corresponding bits of these two words of the same size. So before that one, just we would have a quick revision of XOR gate, because we are going to use XOR operation in order to find the distance, Hamming distance between the receive code word and the send code word, because it is going to tell you the number of bits that are corrupted during the transmission. So suppose if sent and received code word is the same, then 00, then output is 0. Similarly, if the send code word and the receive code one is 1, it means both are similar, so output of XOR it is a 0. But if the two bits are different, that is send and the receive code word are different, then the output is 1. Similarly, if one it has been sent and by receiving it is going to receive it as a 0, it means there is a dissimilarity and the output is 1. So simple, guys. So this is the logic we would come to know by calculating the Hamming distance, whether the error it has been introduced or not. And this is the example that we have kept it for just a revision of your XORing of two patterns. So this is the patterns that now we are going to discuss. As you know, 00, what is the XOR? It is 0. 10, 2 are dissimilar, so output is 1. Similar bits, 1, 1, so it is output is 0. Similarly, 0, 1, 2 dissimilar bits, output is 1. And last, the two ones are there, it means similarity it is there, so output is 0. It is simple. So let's start for calculating the Hamming distance. So you can see it over here, the send code is 000 and the received code it is a 011. So we would have the XOR of this 000 and 011, so you would find it output is 011. It means two ones are there, two change are there. And similarly, the Hamming distance of this send code word and receive code word, it is a 3 over here. In earlier example it was 2, because two ones are there, and in this example we would see 3. See now we are going to make the XOR operation of the send and the receive code word, and you would get the result XORing of these two patterns. You would find it 3 ones are there, it means 3 change are there, 3 corrupted bits are there. So that's why the Hamming distance is 3. Now let's find the Hamming distance for the code words. So the minimum Hamming distance is the smallest Hamming distance between the all possible pairs in a set of code words. So let's understand by with this example. By referring table 2.1, guys, as you know, you can find it this over here, this is a send and this is a receive code word. Similarly, this is the send and this is the receive code word. So in all the pair of these code words, you can find it that 2 it is the Hamming distance. So what is the minimum Hamming distance? It is 2, because everywhere 2 it is there, so no logic it is here. Now in table 2.2, guys, that is 5-bit data. Suppose this is 5-bit data, it has been transmitted, and this is a 5-bit data it is received, and you are going to find all the possible pair of code words, and you would find it over here. For one pair it is 3, for another pair it is a 4, again for another pair it is a 3, 4, and so on. So out of this 4 and 3, which is the minimum? So 3 it is a minimum. So in that possible code words, the minimum Hamming distance in this case is what? 3. Also, guys, just in future or in your further coming lectures, you would get this one. So that's why suppose in the set of code words, to find the minimum Hamming distance in a code, if we want to be able to detect up to S errors, so S possible errors are there, then the Hamming distance between the sent and the received code word, it must be S plus 1. So please remember this one, that the minimum Hamming distance in a block code must be what? S plus 1. So to guarantee the detection of up to S errors in all cases, guys, it should be S plus 1. Now we can look at this criteria geometrically. Let us assume the send code word X, it is at the center of the circle X, which having a radius of small s. Now all the received code words that are created by 0 or 2 s errors are the points inside this circle or on the perimeter of this circle. See, so it is going to tell you all the possible s errors and all other, and remember this is called a invalid or illegal code words, and all other valid code words, it must be outside the circle. Suppose why it is a valid code word? It means that the d minimum must be integer greater than s. See it over here. That is, it should be equal to what? S plus 1. So hope so, guys. So you understood the lecture, that today we have started with the topic called error detection and correction. So while transmission, how the bits are corrupted. So the types of error we discussed, it is a single bit, burst error. We came to know how to calculate the length of the burst. Then we have seen the redundancy, that what is redundancy? It helps to detect the error. Then we have seen the block coding, the basics of block coding. By referring those tables, we came to know that how the errors are introduced, which errors are occurred but not detectable, which errors are detectable with the help of valid and invalid code words. And if we are going to add the more and more redundant bits, then it could also be possible to correct the errors. Then we have seen the Hamming distance, which tells about the number of errors, how the Hamming distance it is calculated. And to guarantee about the detection of S errors, the minimum Hamming distance, it should be what? S plus 1. So this is the assignment. So please note down this assignment. In next module, guys, we are going to discuss about the linear block codes. It is the subtype of your block coding and why we call it as a linear. This is my email address. So it's all about today's lecture. Thank you very much.